Okay, so we ended off the last video with a couple of remarks, and now we'll add a third. So here's what the remark's saying. If you want this notation here, this limit notation, if I want to write the limit as x approaches a of f of x, and I want that to actually mean something, I need the function f to be defined near a. Okay, and this is actually a phrase that has a very, very specific meaning, and we're going to go over that now. So if you say that a function is defined near a, some fixed number a, whatever, really it's just the number that appears in the limit here. If you want to say that f is defined near a, you have to be able to come up with an open interval, which we'll call capital I. So remember what intervals look like, just intervals that don't contain their endpoints. That's what an open interval is. So you need to come up with an open interval I that has two properties. First of all, it has to contain the point A. And second of all, f has to have the property that's defined at every point in this interval that you've come up with, except possibly a itself. We don't actually need f to be defined at a, and really the reason for that is because remember the limit does not care what happens exactly at a. It only cares what happens as x gets close to a. It does not care what happens when x gets to a. Okay, so let's look at an example of this. And before we do that, actually, let me add one more thing, and I want to be clear. It's not that every open interval containing a is going to satisfy this property. It just means that you have to be able to find some open interval I, which contains the point a and satisfies the property that f is defined at every point in that interval, except the possibly at a itself. Okay, so let's do an example. So the first example is I'll define the function f of x, and I'll say it's equal to tan of x. Now this function, I'm going to claim to you, is defined near pi over 2. So pi over 2 is your a value in this example, and tan of x is your f of x in this example. Okay, well, let's draw a quick picture of the graph. I want to just sketch the graph of tan. I got pi over 2 right there, which I'll label here, and we got our vertical asymptote. And what does the function do? It goes through the origin, goes up like this. Maybe I'll label the y-axis. We've got the graph of y equals tan of x here. So this is our x-axis, and then here's the point, right at the point pi, it hits the x-axis and goes down towards that vertical asymptote. Okay, and my claim to you was that f of x, which is defined by tan of x, is defined near this point pi over 2. Well, how would we justify that? We better be able to come up with an open interval I that satisfies each of these two properties. Well, first of all, it had better contain pi over 2. Right, because that's our a value. In this case, this is a. So the interval has to contain our pi over 2. And then also, it has to have the property that this function f is defined at every point in our interval. Well, let's take the interval I to just be pi over 4 to 3 pi over 4. And let's see what that looks like. Here's pi over 4 right here, and here would be 3 pi over 4. Right? If this is pi over 2, where the vertical asymptote is, and this is 0, halfway in the middle would be pi over 2, and then halfway between pi over 2 and pi would be 3 pi over 4. So this interval here that we've just written down is really, if I were to draw the picture, it would be like this interval here. So now you can see from the graph that tan is defined at every point in that interval, except the point pi over 2, because tan is not defined at pi over 2. But that's okay, right? We only require that f be defined at every point in the interval I, except this particular value a that we set as pi over 2. So it's okay that f is not defined at pi over 2, as long as it's defined at every other point in the interval. Okay, now just to convince you that I didn't just choose this interval I at random, right? I had to make sure I chose it small enough, because remember, there's other vertical asymptotes of tan. If we were to sketch a little bit more of the graph, let's say this is negative pi over 2 here, we've got another vertical asymptote here. And then of course the function behaves like that, and then at negative pi you've got this behavior. Just drawing a little bit more of the graph so we can get the point across. And of course there's another vertical asymptote over here if I were to keep drawing in that direction. Now if I drew this interval, if I took this interval to be wider, so wide that say this endpoint got pulled over here, and I made this interval large enough that it contained negative pi over 2 and pi over 2, well then there would be 2 points in that interval in which f is not defined. And then I would no longer be a suitable interval to have this second property be satisfied. So it won't work for any choice of interval I. You have to choose your interval I to be narrow enough. But as long as it's possible to be done, then we say that f is defined near A. So in this case, f of x equals tan of x is defined near A. And let's just spell this out a little bit more. Then f is defined at each x in the interval I except x equals pi over 2. But that's perfectly okay, so there's no problem with that. So that's an example of a function that's defined near a point, in particular pi over 2, but it's not actually defined at pi over 2. Right? So that's the purpose for using this language, defined near a point. Now, if it were defined at pi over 2, that would be no problem as well, but it just doesn't need to be. It doesn't need to be defined at the point pi over 2 in order to be defined near pi over 2. Okay, let's look at another example. If I say g of x is equal to the function 1 over x, well, what happens? So is this, my claim is that this is a function that is defined near 0. So it's certainly not defined at 0, because if you plug in 0, you get 0 on the denominator. So this is not defined at x equals 0. But my claim is that it's defined near 0. And again, in order to come up with our interval, let's draw the picture first. Just to remind ourselves what the graph looks like. You've got the graph of y equals 1 over x. So what does this look like? Well, this has a horizontal asymptote along the x-axis, and it has a vertical asymptote along the y-axis. And it looks something like this. This is just a rough sketch. It's not going to be perfect, but that's okay. So this is roughly what the graph of 1 over x looks like. So we just need to come up with an interval that contains 0 to satisfy the first property, and then we have to have the property that g is defined at every point in that interval, except possibly 0. So let's take I to be the open interval from -1 to 1. So what would that look like? Let's say this is -1, and that's 1. It's going to look something like this. Shade in between. And you can see from the graph that the function g here is defined at every point in that interval, except right at 0, right? There's a vertical asymptote here. I didn't explicitly draw the asymptote because it would coincide with the y-axis. But all the same, there is a vertical asymptote along the y-axis. So g is not defined at 0, but it is defined at every other point in the interval. And actually, in this case, since 0 is the only real number for which g is not defined, you could actually extend this interval to be as wide as you like. You could have taken the interval I to be from -10 to +10, or -100 to +100, and it would still work for the definition of g being defined near 0. It would still satisfy both of these properties. It would still contain 0, and it would still have the property that g is defined at every point in it, except 0. So in this case, you had a lot more flexibility. You didn't have to be very careful when you choose your interval I. But in the first example, part A, we had to make sure that this interval wasn't too wide as to include one of the other nearby asymptotes. We had to zoom in enough that we only captured the local area over here. Okay, so let's finish this off. Then g is defined at each x in I except x equals 0. So that's exactly what we needed. That's perfect. Okay, so now I just want to give you one more example which presents a negative case, so a function that is not defined near a particular value. So you can see here we've written down a function. We've got f of x is equal to sine of pi divided by x. And the claim is it has the following property. If you take any open interval I containing 0, so here's an example of an interval containing 0, right? But my claim is that if you take any open interval I containing 0, for example, it might be much, much, much smaller than the one we've drawn here, from -1 to 1. Maybe it's from -0.0001 to +0.0001, or maybe it's even smaller than that. There's no restriction on how small it can be. The claim is that no matter how small you make this interval I, there are going to be infinitely many values x in that interval, such that this function is equal to 0. So in other words, there's infinitely many places in your interval, no matter how small it is, that the graph of this function crosses the x-axis. So that's not really necessarily obvious, right? So let me give you a bit of a demonstration here. This is let me say it this way. I'll underline this and say check with Desmos. You might be able to get this done with a graphing calculator. If you've got one, that's fine too, but I think Desmos really shines here for cases like this. You might spend a lot more time doing it with a graphing calculator. So I'm just gonna pop over to Desmos. So you can see the address is www.desmos.com. If you've never used it before, I highly recommend checking it out. So we'll go ahead and open that up. Then we'll click on graphing calculator. And then what we're gonna do is we're just going to enter the function f of x is equal to sine. Just type the word sine, put brackets, and then for the pi symbol, just type pi, and then as soon as I hit I, it turns it into a pi symbol. So then I'll divide that by x, and then I'll go over here and close the bracket, and now we've got our function. Okay, so you can see kind of what's happening. I'm just going to now close this so we get a better picture. You can see what's happening, right? As it looks kind of like a sine wave, but it's skewed, right? And that's when you plug pi over x into sine, you're going to get a weird warped shape of a sine wave. And over here, if I start at positive 10 and move my way to the left towards the origin, you can see it's kind of curving up, and then it's curving down and up and down. So if you just look at the fact that it's going up and down and up and down, it is definitely oscillating. But it seems like the further you are away from the origin, the slower the oscillation happens, so the lower its frequency is. Its frequency seems to be dependent on how close you are to the y-axis. So what happens here? What if we took, you can see if we took an interval maybe from, I don't know, this would be -1. If this is -2, this must be -1. So this would be -0.5 right here. And then this would be +1 because that's 2. So this is +1 and this would be +0.5. Most of this oscillation happens between -0.5 and +0.5. So if we took that to be our interval, it certainly looks like this graph is going to cross the x-axis many times in that interval. But you might ask the question, well, what happens if we zoom in, right? Maybe when we zoom in, maybe eventually it calms down. Maybe eventually you get close enough to 0 and the graph gets all this oscillation out of its system, and then it calms down and is well behaved. So let's zoom in. You can just use your mouse wheel to do this. We'll just zoom in at the origin and see what happens as we get closer. Maybe if we just keep on going, maybe eventually it will calm down. And it just seems to get worse. The more you zoom in, the faster the graph oscillates. In fact, if you get now to this point, you can see the scale over here. You can see this is from -0.002 to +0.0002. If we take that to be our interval, which is really small, you can't even see what's happening. The graph is oscillating back and forth so rapidly that you literally can barely see the whites between the graph anymore. It almost looks like it's pure red. Right? So that's the idea. The closer you get to the origin, the faster it oscillates, and that's why no matter how small of an interval you take about the origin, so no matter how small you take your interval I containing 0, there's going to be infinitely many values where this graph hits the x-axis. Okay, so that's the justification for this fact here. This should be a bracket there. Okay, so that's why for any open interval I containing 0, there are infinitely many values x and I such that f of x is equal to 0. Okay, so this actually isn't going to be the function that we work with. F of x is equal to sine of pi over x. That function actually is defined near 0 because it turns out that 0 is the only place where it's not defined. So note that having a value x such that f of x is equal to 0, that's not the same thing as f not being defined. But if I define a new function, so take g of x equal to 1 over f of x. So really I'm talking about the function that's g of, I'll add this in, but you don't need to. You could say this is 1 over sine of pi over x. If you define this to be your function g, now g of x is equal to 1 over f of x. Remember, anywhere that f of x is equal to 0, g of x is going to be undefined. So this function is not defined near 0. And the reason is because any interval containing 0 is going to contain infinitely many points such that f of x is equal to 0. Or in other words, it's going to contain infinitely many points x such that g of x is undefined. So let's spell that out. The reason is any interval I containing 0 also contains infinitely many values x such that g of x is not defined. Really, if you take a look, you'll see that all I did is I just rephrased this property here in terms of g of x being undefined here instead of f of x being 0. So that's an example of a function that's not defined near a point. And again, we're talking about the function g of x is equal to 1 over sine of pi over x. Okay, so that's what it means for a function to be near, that's what it means for a function to be defined near another point.